From what the syllabus says, you all should be talking about induction at this point. So I want to go over a brief introduction to induction and then provide you with an example of an inductive proof. So here's kind of the main idea behind induction. If you want to prove a statement that has the form of for all n greater than 1, for example, and here we're talking about natural numbers, you'd either have to start that proof by just taking an arbitrary element n in the natural numbers and then proving the claim directly from there, or you can use induction. And induction is a great way to simplify a lot of these proofs that would otherwise be extremely complicated in order to prove it for all n greater than or equal to 1, for example. And the main structure behind any inductive proof is going to be the same. You're always going to start by providing a base case, which is sort of going to act as the foundation on which all of the rest of the induction takes place. And then from there, you're going to suppose that you've got the result proved up to some point. And so let's say that that thing is k. So you're going to suppose that you've proved everything up until the case when n equals k. And now using that hypothesis, using the hypothesis that you've built this stack on which you've proved everything, then you're going to say, okay, we've got it for case k. Now let's show it for the case for k plus 1. And what induction does is it says, because we've already built this tower, we have that foundation on which to build this k plus 1th case. And so that's what the real meat of the proof is going to be, is you're going to prove that you get the result on the next step in that tower, case k plus 1. And this is daunting at first. It's intimidating and confusing. And the analogy that I want you to have in mind is that you're building a tower and you are trying to build the next level of this tower. So here you're trying to build that next case k plus 1. You have to start your tower somewhere. And that's what the base case gives you, is it says, let's start here, and then we're going to show that we have this foundation on which to build. And then you're going to say, okay, let's suppose that I've been given some amount of this tower already. I don't really know anything about this tower, except that I know it exists and that it works. And then from there, using that tower, we're going to construct this final block on the top. And this is going to get us the result that for any n greater than or equal to 1, you're going to be able to say, well, okay, let's suppose that we've got the result for everything before n that we're looking at, and then use this inductive proof to get what we want. So here's an example that I want us to run through. So the example is to prove that the sum of the first n odd natural numbers is n squared. You might go about this by saying, okay, well, let's let n be some natural number, and then let's take the first n odd natural numbers, and so that means we're going to take 1 plus 3 plus 5 plus, I guess it would be plus 2n plus 1. And then you'd come up with some formula. You'd say, okay, well, that equals the sum of 2k plus 1, where k equals 1 to n. And then you'd do some more gymnastics, and maybe somehow you'd find out that that equals n squared. But the step from there to there isn't going to be necessarily obvious or apparent. And what induction does is it says, well, let's pretend that we know that we've got the result up to this point, 2 times n minus 1 plus 1. Let's suppose that we know that this thing is actually n minus 1 squared. So here the n minus 1 is what's going in there. So we're going to suppose that. And then we're going to say that if we then add on that last term, that whole thing is going to be n squared. So that's the structure of the proof, of what an inductive version of the proof would look like. So let's write it out a bit more carefully. In our inductive proof, we have to do these 3 steps. We first have to provide a base case. And our base case is going to be the thing that everything else rests on. So it should be kind of the first possible case. And because we're talking about odd natural numbers, that base case here is going to be the case when n equals 1. So here's our first step is the base case. And so that's going to be n equals 1. So we have to prove that the claim holds on our base case first. And so here our base case is n equals 1. So we're going to show that the sum of the first 1 odd natural numbers is n squared. And that really means we want to show that the sum of the first odd natural number, which is just the first odd natural number, is n squared equals 1. That should be pretty apparent. The first odd natural number is just 1, and so the sum of the first 1 odd natural number is just the sum of the number 1 time, just equals 1, which, yeah, that equals n squared. And so that proves the result for the base case. So now before we go about doing our inductive hypothesis and proving the result, we're going to say, let's now start by saying, let n be some arbitrary natural number now. Okay? And what we're going to suppose now, as our inductive hypothesis, we're going to suppose that the result holds for n minus 1. So here we're going to suppose as our inductive hypothesis that the sum of the first n minus 1 odd natural numbers is n minus 1 squared. So take a look at the original problem, see if this makes sense, and see if you can understand how this is an inductive hypothesis. Here we're supposed to prove that the sum of the first n odd natural numbers is n squared. And here in my inductive hypothesis, I'm supposing that the sum of the first n minus 1 odd natural numbers is going to be n minus 1 squared. So what I've done is I've supposed that the result holds for n minus 1 as opposed to n. And now I'm going to show that it holds for n as well. So now we're going on to the inductive step, which uses our inductive hypothesis from before to prove the result for n. So we're supposing that we've already got the result true for n minus 1, and we're going to show that it holds for n now, okay? So let's first figure out what the nth odd natural number is. The first odd natural number is going to be 1. The second odd natural number is going to be 3. The third odd natural number is going to be 5. So here we've got this is the first, this is second, this is third. And you can figure out a pattern that the kth odd natural number is going to be just 2 times k minus 1. Okay, see if you can convince yourself of that using this pattern here. But what we're going to do is we're going to say that the kth odd natural number is 2k minus 1. And let's call it O sub k. Okay, that's the letter O, not the number 0. Okay, well then the sum of the first n odd natural numbers, that's just going to be is the sum from k equal to 1 up until n of this O sub k. And our goal is to show that that sum there is actually equal to n squared. By the inductive hypothesis, we're supposing, though, that... Okay, so by the inductive hypothesis, we suppose that the sum up to n minus 1 is going to be just n minus 1 squared. Okay, that's what the inductive hypothesis is telling us. And see if you can convince yourself of that. That this thing here is the same thing as the inductive hypothesis highlighted in blue there. Okay, let me try and keep those both on the screen. Right, you're supposed to see that the sum of the first n minus 1 odd natural numbers is in fact n minus 1 squared. That's what we're supposing is true. Okay, well now that we've supposed that, writing down this sum up here becomes a little bit more manageable, because we can just write that this sum, okay, is actually just equal to the sum from 1 to n minus 1 of okay, plus that last term that we're dealing with, plus the nth term. Okay. Well, and now this just equals n minus 1 squared plus that nth term. Okay. And again, this here is the same thing as the stuff that's highlighted in blue. That's why these two lines are equal. Because we're supposing by the inductive hypothesis that that's true. And then from there, we say, well, by our definition of the nth odd natural number, this ON is just going to be 2n minus 1, right? That's what we said O sub n is, right? We said up here that the kth odd natural number is 2k minus 1, so we would call that OK. So that means that ON is really just 2n minus 1. It's the nth odd natural number. From there, it's really just bookkeeping. You say, okay, well, I know how to simplify this. We've got n squared minus 2n plus 1 plus 2n minus 1. And, well, lucky for us, it looks like we've got some cancellation here. 2n's disappear, the 1's disappear, and we're left miraculously with n squared. And so we've shown that the sum of the first n odd natural numbers is in fact n squared. Now you might be worried, well, how do we know that this thing here is true? We just sort of started supposing that it was true. And yeah, you're right. We did suppose that it was true. That's what our inductive hypothesis was. But this all works because we showed that we had a base case. And so we built up this tower in some sense where we started with this base case. And then I said, okay, I may not know how to prove this one, but I'm going to suppose that I've already been given everything that comes before it. And then I'm going to show you how to build this last piece. And you can do that. You could use that same argument for every single block on this tower until you got up to the point where you're proving this k plus 1th case, or in our case, the nth case. And so that's the general structure of an inductive proof. You start with your base case, you prove that the result holds for that base case, and then you use the inductive hypothesis to build up on that base case to say, well, okay, let's suppose that we've got it for everything that comes before the nth case, and let's prove that the nth case holds as well. So that's the general structure of an inductive proof. I hope that this was instructive. And again, check out the practice problems that are on the website, and feel free to come and ask me any questions that you have.